So this video is about solving rational inequalities, and we're going to do it two ways. We're going to do it first by graphing, and then we're going to use a table. And that's the method that I think we should stick with, because when we're solving rational inequalities, it can get pretty complicated doing it graphing-wise. So we'll start off by graphing so you can see what's going on. Let's say I've been given two functions. Functions one is f at x is 1 over x plus 1, which we know is a reciprocal function. And g at x is equal to 5, which is just a linear horizontal function. The question is when is the f at x function less than or equal to the g at x function? So I've already started us off a little bit by setting up this reciprocal function. So it's the reciprocal to the line x plus 1, meaning I have an x-intercept or y-intercept at 1 here, and remembering that reciprocal functions have an asymptote, a horizontal asymptote always at y equals 0. So let me just make sure I label my axes here. Because I have a denominator of x plus 1, I also have a vertical asymptote at x equals -1. And here's the other fixed points for the reciprocal function, and it's going to look like that. Okay, we want to compare that to the g at x function, and the g at x function is a horizontal line that goes through at 5. So, like that. All right, so that's g at x. Good. And so well, if we're walking from left to right along the function, we're looking for when the purple is less than or equal to the red. So the purple is less than or equal to the red all along here, all along here, all along here, until I hit this asymptote. And then I have to jump over the asymptote, and then again, all along here, all along here, all along here, all along there, the purple is less than or equal to the red. So let's see what that means. Let's see if we can answer this question. So let's see if we can answer this question. So f at x is less than or equal to g at x when my x values go from -infinity all the way up to the asymptote. And then they have to stop because nothing's happening at this vertical asymptote. So from -infinity all the way up to -1, then the function is less than or equal to. And because it doesn't actually hit -1, we're going to use a round bracket. Or it also happens from where these two lines meet, which is the point of intersection, all the way up to +infinity. And there's one little mistake that I made here, and that is because we're talking about less than or equal to, that at the point of intersection, it actually is equal to that value. So we can use a square bracket there. Okay, but because infinity and -infinity, we actually don't hit those numbers, we use a round bracket, and at -1, it's an asymptote, we don't hit that either. So what does that mean we have to do? Well, of course, that means we have to find out what the point of intersection is. So our next step then is to set f at x equal to g at x. X plus 1. And I want to see when that actually equals 5. So I'm going to do some multiplying here. I'm going to take the x plus 1 and multiply it on both sides. So it's going to leave me with simply a 1 on the left-hand side and 5 bracket x plus 1 on the right-hand side. I keep going and I get 5x plus 5, and we do the math, and we're going to subtract 5 on both sides, so I get -4 is equal to 5x, divide everything by 5, and x turns out to be -4/5. So the x value at the point of intersection is going to be at -4/5. I don't need to calculate the y value because I'm just looking at when x is a member between. So now that I have this value of -4/5, I can plug it back in here to my point of intersection. So let's erase what's already there. We don't need to call it point of intersection anymore. We know that the answer to that is -4/5. There we go. And so we have solved the question of when f at x is less than or equal to g at x. And this is how we would do it graphically. Now it gets a little bit more complicated when I'm not using a horizontal line, or I'm going to be comparing two functions that are both rational functions. So we're going to show you a way to do it using a table. Okay, so now we've been given the inequality. We're going to solve x minus 2 is less than 8 over x. And I have to be careful that I don't just approach this algebraically. What our intention, or what we might, when we first look at this, we might think, oh, this is easy. I'm going to multiply both sides by x, and I'm going to solve the inequality. The problem with that is the following. Since the x is in the denominator, and I would be multiplying both sides by x, when we multiply by an inequality, if you remember, if we multiply by a negative value, then if you remember the rule, to keep the inequality working, we'd have to switch the inequality sign. And if I was multiplying by a positive value, I wouldn't have to switch the sign. It stays the same. And how do I know what x is? Well, x is going to be values that are negative and that are positive, so we can't just solve this algebraically. So in this way, we either have to set up a graph or we have to set up a table. Okay, so if you remember back in our graph, we needed to find the point of intersection, because that's when things changed, at the point of intersection. The second place where one function is going to become greater than the other function is at asymptotes. So what we're going to do is we're going to find out all of the points of intersection and all of the asymptotes, and that's going to help us set up our table. Okay, the first thing we want to do, though, is we want to get a 0 on the one side of the inequality. I cannot multiply by x because I don't know if x is going to be positive or negative. So what I have to do in order to get a 0 here is I'm going to subtract 8 minus x on both sides. And that's going to give me this. X minus 2 subtract 8 minus x, or 8 over x. And that's going to be less than or equal to 0. So I subtracted 8 over x on both sides. And that didn't make me have to change the inequality sign. If I'd have multiplied by x, I don't know if x was going to be negative or positive, so I don't know if I should have switched the sign or not. Okay, so at this point, I'm going to need a common denominator. So I'm going to, let's write x minus 2 like this. And we're going to want to put that over x. So in order to put a denominator of x on the bottom of that, I need to multiply the top by x as well to keep the ratio the same. So it's going to be x times x minus 2 all over x minus 8 over x, and all of that's less than 0. And then I do the math. Then I'm going to have x squared minus 2x minus 8, and all of that's over x, and that's going to be less than or equal to 0. Okay, what I can do at this point is I can factor the numerator. I can say what multiplies the negative 8 and at the same time adds to negative 2. And that's going to give me x minus 4 and x plus 2 over x is less than 0. Okay, so now we've got this form here, which is equivalent to this up here. They're the same thing, but we just gathered our terms together so that I could get a 0 on one side, and that just makes it easier to solve. All right, now if you remember the two things that we need to determine, and they are our asymptotes and our points of intersection. So let's determine those now. Let's determine our vertical asymptotes. So taking a look at this function, the only vertical asymptote occurs at x is equal to 0. That's going to be our vertical asymptote. And that can cause something to happen when we're comparing the two functions. The other thing we have to figure out is our point of intersection. And for that, we go back to the original two functions. We set them equal to each other to see what the point of intersection is going to be. So I'm going to have x minus 2 is equal to 8 over x. At this point, because there's no inequality sign here, I can multiply both sides by x. And so that's going to give me x times x minus 2 is equal to 8. And doing the math, it's going to give me x squared minus 2x minus 8 equals 0. So I have x minus 4, x plus 2 equals 0. So x is equal to 4, and x is equal to negative 2. Okay, so now I also have my point of intersections. So 0, 4, and negative 2 are significant points because those are the areas on the function where they're going to change from being greater than or less than. All right, so let's just extend the page here. And now we're going to set up a table. And this is just like polynomial functions. In the table, we're going to put the asymptotes and the points of intersection in the order that they occur going from left to right. So I'm going to put in my negative 2, I'm going to put in my 0, and I'm going to put in my 4. All right? Okay. Then, what I want to do is I want to determine some values that fall on either side of these fences. So what's happening in my function before negative 2? Well, let's check that out by using negative 3. What's happening between negative 2 and 0? Well, I don't know. Let's check it out by plugging in the value negative 1. What's happening between 0 and 4? Let's try 1. And what's happening after 4? We try 5. Good. And then what I'm going to do is I'm going to go back to the equivalent form of my inequality, and I'm going to put down all of the factors. So if I have an x minus 4, an x plus 2, and all of that's dividing by x, what I'm trying to determine is my result going to be positive or negative? And that's going to tell me whether or not this is going to be less than 0 or greater than 0. Okay, so let's do this. If I plug in negative 3 into here, I don't even have to really do the math and figure out what that is, but a negative 3 and then I'm subtracting 4 more, it's going to give me a negative result. If I plug a negative 3 into here and I add only 2, then I'm still going to be in the negatives, and a negative 3 times the x gives me a negative. So that means if I have a negative times a negative divided by a negative, my result is going to be negative. So an odd number of negatives means it's negative. So already I've found an area that's less than 0. Let's see what happens at negative 1. So after I hit this point of intersection, what's happening? If I plug in a negative 1 and I subtract 4, I still have a negative. Plug in a negative 1 and add 2, oh, there's a positive. A negative times x gives me a negative, and 2 negatives cancel each other out, plus a positive. Then between negative 2 and 0, my function's going to be greater than 0. All right, along my x-axis again. Now we're looking at 1. 1 minus 4 is negative. 1 plus 2 is positive. 1 itself is positive. So 2 positives, 1 negative. That negative has nobody to cancel out with. It's an odd number of negatives, so the result is going to be negative. And 5 minus 4 is positive. 5 plus 2 is positive. And 5 itself is positive, so it's positive. So therefore, to answer this question, I can see that x minus 4 times x minus 2 divided by x is less than or equal to 0 when, so we'll say the function is less than 0 when x falls less than 2. So x is between negative infinity and negative 2. Now, because we're talking about just less than, the negative 2 would not have a square bracket. It would just have a round bracket. Or, when else is this going to occur? This is also going to occur between 0 and 4. So also when x falls between 0, which was my asymptote, and 4.